Okay, well, hi everyone. Welcome to week 4 of Cyber Academy. Today we will be presenting binary analysis. My name is Savannah.
Oh yeah, I'm Salma, by the way. Those of you who don't know. Let me just go through a couple quick announcements really quickly. Week 5 is just like our event stuff. Week 5, we do not have anything going on. Break, midterms, good luck, don't die. Week 6, though, we have a bunch of stuff going on as per usual. Tuesdays, we have our PPR practice extra special this time because Will, ex-cyber alumni, I don't know why I put his fund on there, but that's his like other name. He's part of like a really good CTF team, used to be in cyber. He's coming to the talk Tuesday 6 to 8, Ackerman 3517. Be there. He's very cool, very experienced in like cryptography and stuff. Next, this is also in 2 weeks from now. We have Cyber Academy, same day, same time as what we have now. It's on binary exploitation tools. So like if you're in CS33, think Attack Lab. That's what that's going to help you with. Once again, we have our like DEF CON interest form. If you don't know what DEF CON is, big security convention, very cool. We might be able to get that reimbursed if enough people want to go. So fill that out if you're interested. It's going to be over the summer. I don't remember the exact dates. I think they're on the form. And then last of all, the CS Town Hall is going to be, what is it? Wednesday, 6 to 7 of week 6. So it is at the same time as this. However, even if you're not able to make it, please fill out the form, put in questions for faculty. It's really important for us to like get things changed in the CS department. The link is there, it's on the slides. Please fill it out. Shameless plug, ask for more cybersecurity classes. But yeah, we would appreciate if you fill that out. The department likes it when more people fill it out, because if only 80 people fill it out, they go, that's not enough, and they don't change anything. So yeah, shameless plug, and without further ado.
So what exactly is binary analysis? So binary analysis is a subset of reverse engineering. So we're going to be looking at code that has been compiled down to like the binary form or the machine level. So this is binary, what the computer understands, pure ones and zeros. We can't understand that. I mean, you can put it into a binary converter, but it says, can you read this? You wouldn't be able to tell just from looking at it though. So our focus is going to be one level above the pure binary. So it sits, like I said, in between the pure binary and higher level programming languages like C++ and Python. So there are 2 types of assembly, AT&T syntax and Intel syntax. Now, as the name suggests, really only the difference is in these 2 types of assembly are the syntactical differences. And so even though Intel syntax is more commonly used around the world, like a lot more, we are going to be focusing on AT&T syntax, since that's what CS33 is teaching, and we don't want to confuse you.
Sorry.
So in assembly, there is data stored in memory addresses and registers on your computer. So some examples of registers that you might have seen or encountered before are EAX, RDI, etc. And so the way that assembly works is you have your instruction, your source, and your destination. Depending on the instruction, you might leave off like some of those, but this is like the basic form. So in your source, you can put in like literal values, like say just 1, something that won't change, or like just the number 2. These are denoted with a $sign. Then for both your source and your destination, you can put in the value held in a register, which is noted with a %sign. And then also for your source and destination, you can put in the memory address held in your register. And this is noted with like a parentheses and a %sign. Think of like this, just like as your register holding a pointer, and you're accessing what the pointer holds. And then now for like the source or destination, you might see this like funky syntax. I just put in like random letters here, but this is what it comes out to. Not intuitive at all, but this is what it is. And then I have linked a handy cheat sheet of like different registers and instructions if you want to look at that later. Okay, so now I'll talk a little bit about common assembly instructions. There are a lot of them, so I'll not go over all of them, just give you like a brief rundown of some of the common ones. So for the basics, we have move. So in assembly, you always go from your source to your destination. So if you are moving, for the example, you can move 1 into your EAX register. There is also LEA, which stands for load affected address. You're kind of like doing manipulation with the address. You're not like moving like the move does, which some people get confused about that. There's an example up there. There's also a push command or instruction where you push the value of your register onto the stack. There's also the ret instruction, which basically you like return from your function. And then there is call Q, which you call a function, and then like the function will be in those like little greater than equal to sign, like showing you where the function is or what the function name is. And then there are also a lot of different types of jumps. So what jumps do is they jump to a specific part of the code if certain conditions are met. So for example, you might jump to the section .l4. Now you may be wondering like what's the difference between jumps and call queues. So call queue is really for calling like different functions, whereas jump is more used for like if you have like while loops or if statements where you're like going to different parts of the code rather than just a function. Then there's also conditional moves, which it copies the source to the destination if certain conditions are met. Here are some examples. So then like an actual example is like, oh, you compare the value of RSI and the value of RDI, and then cmove LE, like move if less than or equal to. So you will move the value of you will move the value of RDX into RAX if RSI is less than or equal to RDX. And then I think this is the last, like just the basics of assembly. So here are just some common registers that you will see because it's good to know what they mean. So RAX is where your return value is stored. So like what a function is returning or something. And if you have functions, these are the different values assigned to different arguments. So like the first argument in your function would be RDI, the second argument in your function would be RDX, etc. Then we also have RIP, which is the instruction pointer. So like the next instruction that the computer is going to execute. And then we also have RSP, which is your stack pointer.
Don't have RVP on here as well, but that's another one for the base pointer. Really quickly, why does this matter? I'm not going to read all this stuff, but at the like fundamental level, being good at reverse engineering will make you a better programmer overall because it makes you better at understanding the fundamentals of how programs actually work at a low level, which I think is a very good skill, very transferable. Very all right. Now we can move on to some tooling, some new stuff maybe. So first of all, we're just gonna Savannah, can you do the slides?
Oh yeah, sure.
Well, yeah, so first of all, we're just going to talk about GDB really quickly. GDB, you've probably used it before. If you haven't, though, that's okay. We're going to talk to you about it a little bit. GDB, it stands for GNU Debugger, and basically what it does is it kind of shows the assembly of an executable and you run it step by step. It's essentially just a debugger, but for like at the assembly level. So there's a couple different for different operating systems, you'll have to run it differently. If you need help with running it, ask us. But that's how you can run stuff. Next. Okay, and I'm not going to talk an insane amount about extra GDB features, but I'll talk about some stuff later. So I guess now we get into some new stuff that you might not have heard of before. This is Jeff. It stands for GDB Enhanced Features, and it's an extension that was written for GDB because GDB is really old. So in order to make it more modern, cooler, more up-to-date, people made Jeff, which makes GDB easier to use, add some new features. Pretty simple to install, very well documented. Click on that link to figure out how to do it. Again, if you need help, ask. But yeah, look at this. This is the GDB. If you run a program, this is a program called Minibomb. I'll be showing you guys a demo of this later. It's a challenge on our website, actually, so this will help you get some extra points if you want. But this is what happens when you hit run after setting a breakpoint at main Minibomb with just GDB. Very boring, very sad. Click again. Look at Jeffs. You get a whole lot of extra information. It might be a bit blurry because of the text size, But what Jeff gives you, it gives you, for example, you could see up there, RAX all the way down to like R15. It gives you all the registers. It tells you when they're modified. If you have like a string in one of your registers, it'll actually go all the way to that string. So you could see like RSI holds like my directory with the executable. It'll show you like the assembly as you're going. You can see it's an Intel syntax right now. I'll change that later. But overall, it makes it a lot easier. You can do all of this in like regular assembly as well. Like if you want to show your registers, you can type IR info registers. If you want to show this kind of assembly view, you can type dissess. There's other stuff that you can do it, but Jeff makes it a lot easier. That's why I think it's pretty good. Also, you can install it on the Linux server. It's specifically only Linux server 15. All right, and then we're going to do some quick review right now of the GDB X command. I think we might have reviewed this a bit last week, but we're going to cover it again. So it's pretty important to understand. But essentially, the X command, what it does is it lets you display like information in registers or in memory. The X doesn't actually stand for the display. It stands for examine. Thank you. But essentially, I'll kind of run through this for you. It's kind of similar in other scenarios, but you'll do the X slash at the beginning of every single display command. And then you can have this optional parameter in the front. It's called like it's some number. Here it's 20. That just its defaults to 1, and essentially it's how many groups of whatever comes next you want to display. Next, you'll have this parameter that is here. It's W. That stands for word. It means I want 4 bytes. You can also put H for 2 bytes. B for 1 byte, G for 8 bytes, and then S for string, which will, what string does, it's not a specific size, it just goes until it hits a null byte. You can also do I if you think that there's an instruction in memory that you want to look at. But yeah, these are generally pretty useful. And then last of all, you have this X right here currently, which stands for hex. And essentially that just changes the format of whatever is being displayed. By default, it'll show you decimal. Usually decimal is not the most helpful, so I'd recommend putting hex X at the end of everything that you do. And then last of all, you can see right there that they are accessing something in a register. So they've got, $ register. And then you can do an offset of that register too if you want. Like here we do RSP minus 0x40. You can do plus 0x40. You can just do RSP, that's fine too. And then if you want to access, say, like a location in memory, you can do star memory location, and then it'll access that location in memory. But yeah, feel free to try that out in GDB as well. It's pretty useful for debugging. Next.
Okay, so now I'm talking about control. So control flow graphs are really helpful tools that visually show you the steps of an executable. So it's much faster to read because, again, it's all visually laid out. And this allows you to really be able to see where the path the code will take depending on certain circumstances. So there are 2 main tools to use for control flow graphs. The first is Cutter, and the second is Binary Ninja/Binja. So there are 2 forms of Binja you can use. You can actually download the demo version of Binja, which is free. Or you could do Binja Cloud on your computer. You don't have to download anything at all, but the only downside is you're stuck with Intel syntax. Okay. So if you don't know Intel syntax, don't use it. But if you're familiar with it, it might be good to look into.
And then Cutter is downloadable.
Oh yes, Cutter is downloadable.
Yeah. Also, by the way, if you have any questions as we're presenting, please feel free to ask them, or if we're going too fast.
So now I'm just going to show you why control flow graphs are super useful. So we have this big long wall. Okay, it's not super big, but it's still like a wall of text. And we see like up above, this is our whole main function. So we see that if we go up to here, we have a jump instruction to this value right there, which we search for it. We're like, oh, okay, it's right here. And then we're like, oh, okay, if we hit this condition, we jump to this value. Where is that value? This value is somewhere up here. So it's not that bad to try to decipher if you have something small like this. But if you have something bigger, figuring out where you will jump to is kind of hard and confusing to just look at first. You just have to sit down and really understand it. But this is a control flow graph. As you can see, it is much easier just to look at and understand what's going on. So the blue arrows represent unconditional paths. So the path is always taken by the blue arrow. And then green arrows is a path like taken if this thing is true. And then path not taken would be the red arrow. So we can just see just by looking at the control flow graph, okay, we go through like this part of the function, and then we always jump to here. And then if we take the path, we go here, then it loops around. It's some sort of while loop. We can tell just by looking at it, since like you always loop back around. And then if we don't meet a certain condition, then we'll break out of the while loop. So we can just figure this out in like 2 seconds instead of having to sit down and read through a bunch of numbers and stuff. So it's really helpful. And like I said before, this was a small program, but you can imagine how much more helpful this would be if we had a super large program.
Slide on that.
No.
I didn't skip slide on that. It's just, oh, sorry, never mind. We're not too all right, sounds good. All right, that's also really helpful for other cases, by the way, like switch statements, for example, recursion. Recursion maybe not so much for control flow graphs, but still very helpful for other types of interesting control flow. But I guess one more feature that we could talk about that Cutter does this, Binary Ninja does this. Wait, it might do it with the demo. I don't really remember off the top of my head, but just use Cutter, is you can do something called patching binaries. So basically, you can rewrite the operation codes that are being executed. So like, let's say there's an instruction that you don't want to execute in your program, like ever, something that will do something bad, something that will, just a hypothetical scenario, send a network call to the CSNet server that you exploded a theoretical bomb. I didn't say anything about that, but you can remove that functionality by just replacing those instructions with nots, which in hex that's 0x90, and that just stands for no operation. It does nothing. It just slides right through. Or you can even go in and directly change the code logic. Don't do this on your assignments, BTW. And we will show you some of that later. But yeah, it's demo time now. I need to share my screen really quickly. Sorry, give me one moment. All right. All right, let me share my screen. All right, that's good. We can see it. All right, so what I'm going to be talking to you guys about is just this program that's called, Minibomb. You can find it on our platform of challenges. I'm just going to kind of walk you through it, and we're going to learn about some of the stuff that we just discussed. Here, especially if you have any questions, feel free to stop me and ask me, and we'll work through it. But yeah, so right now I've just opened up like my terminal. I'm in like my cyber directory. I have a program called Minibomb in there. So first of all, we can just run it and see what happens. So you see, it's asking us for the password. Is this text too tiny? All right, 1 second. Sorry, I need to get a better terminal. Is this better? Okay. You can see it's asking us a question, what's the password? We're right here, we can put in some input. So we can just try something here. Let's try password 123 because that's more secure, trust me. So we'll try password 123. Boom, we get this message, boom, the bomb exploded. You lost 100% of your grade. It went from 0 to 0. All right, so the first thing I'm going to show you guys is this. Currently, it's just a print statement. It just prints, boom, this bomb exploded. It doesn't do anything malicious. I know that because I've seen the code, but we might just not want this to run. We don't want people to know that we exploded our bomb because it's shameful. So we can go ahead and actually patch that out. So what I'm going to do, first of all, is I'm just going to open up Cutter, and I'm going to open up Minibomb in Cutter. So we're going to do that, and we're going to do this thing called load and write mode, which is going to allow us to write to the binary. Sorry if this font is tiny, by the way. We'll let it load, let it do its thing. I'm going to quickly walk you through this. We've got a bunch of different functions right over here. A lot of these are like just functions from the C library, like fgets, fopen, puts. We can kind of ignore those. You've got these initial functions too. But the ones that we really care about are the ones that are defined like by the program itself, like explicitly. Like we have main right here, which is just the main routine of our function. We're not going to go through it in too much detail right now. We'll talk about it a bit more later. But you can see right here, it's asking like, what's the password? And then it asks us another question later on, what's my favorite number? We didn't get to it because we exploded the bomb. And right now it's in this nice like control flow graph format because Cutter, I believe, just defaults to showing you that. But yeah, we can see we have some more functions here. We have diffuse, and then we have explode, which we think that's probably where our exploding print's coming from. And you'd be right, it's right here. So what we can actually do is we can just go in, we can go edit, and we can just click NOP instruction, and it just replaced the entirety of just putting that string in with NOPs. We can do the same for this puts instruction, which will put it onto the terminal. I think I explained it earlier. Do you guys have any questions about what NOP does? I can explain it again. Okay, essentially it just does nothing. NOP stands for no operation. But yeah, so we can just go ahead and do that. We've gotten rid of placing and putting that string, and we can just save this. And let me close it. I said, let me close it, save. I'll open that up later. I have to open it up again. But now this time, if we go mini bomb and we go password 123, which we know is not the right password, it doesn't print anything. Now, what I just did, like, it's kind of irreversible unless I save the stuff, I think, but it's fine. We don't need that explosion confirmation. We'll know it exploded. So yeah, that's an example of patching binaries. It's pretty cool. You can use it for other stuff. You can do more complex patching of binaries, like actually replacing the instructions with useful instructions instead of just NOPs. But we're just using NOPs for now, since that's the simplest thing, just does nothing. Yeah, so what we've just done is we've done that bit, but now we can go ahead and actually start working on this function, right? So we can just open up Minibomb in GDB, and I have Jeff enabled, so it's going to look a bit different from your normal GDB. Can I close this thing? Oh, no. Hide this in the corner. I don't remember how it works, but yeah. You can kind of see right here, I've opened up GDB. It's loaded all the symbols and commands. I can do like info functions, and that should work fine. And it shows all the functions. You can see the C functions. You can also see the ones that were just defined by who made the program, like explode, diffuse, this magic function that we might have to think about later, and then the main routine. All right, so like what we usually do when we're debugging in GDB is we just put a breakpoint at main so that we don't like, what this will do is when we start running, it just stops the program right away so we can step through stuff really nicely. So we can go ahead and do that. And then we can just take a quick look at main before we do anything, because some stuff you can just statically analyze. Oh, sorry, main. Oh, sorry, by the way, this is in Intel syntax because everything defaults to Intel. If you don't want it to be Intel, you can do set disassembly. Sorry, does anyone know how to make this? Oh, the bottom panel is, never mind, we're good. The bottom panel is only on my screen. Let me move it on my screen. All right, you can do set disassembly flavor, ATT, and then if I were to do this again, it would do it in good old AT&T syntax. I'm sorry to any Intel supremacists, aka probably half the people here, but this is just what we're going with for now. Feel free to keep your stuff on AT&T if you want, or in Intel if you want, but just for demonstration purposes of universality of things, we're going AT&T. All right. So we'll just take a quick look at this before we do anything. Let me know if you guys like notice anything, by the way, if you need the font bigger. But you can kind of see we're doing the set buff as fgets, which this kind of combination of stuff generally means you're putting a string or something onto like the display, and then you're getting onto standard output, and then you're getting something from standard input. So I'm giving something to the user, and then I'm asking for something from the user. And then just going down, we can see we do this strcmp, which stands for string comparison. It's a C function that looks at two strings and checks if they are equal or not. And then we call test, which, by the way, if they're equal, it returns 0. We call test, which what test does, it checks if two registers are the same, and if they are, it'll return 0. And then we're good. And then we will go jump equal. So if this test passes, we will jump past this explode call. We'll jump to main 122. Otherwise, we'll hit explode. Right. So I'm just going to kind of stop looking at main for now, just from there. We can look at the rest later if we just want to just stare at it. But yeah, does anyone notice anything just by looking at this that's on here that might seem kind of interesting? That's on here that might seem kind of interesting. All right. Whoever named their variables here wasn't very secretive about it. But you can, sorry. But yeah, you can kind of see here that there's this move call right here that's asking for like some location in memory, and it's moving that into RDX. And then what GDB does is it tells you actually what's at that location. And what's at that location happens to be this thing called secret, this variable that was declared. That's something that we might want to keep an eye on. For now, I'm just going to be lazy. I'm just going to put a breakpoint here, and then we're going to just run and see what that is. But we can also just take a look at it ourselves in a bit. I think I already put the breakpoint at main. Yes, I did. All right. So we're going to put a breakpoint. I think I need the star. Breakpoint there at that move instruction, and then we're just going to start running things because I'm impatient. All right. Because the font is kind of big, you can't see the entire thing, so I'll scroll up. But you can see this is what's in our registers right now. Nothing like particularly of interest because we haven't done that move with the secret string or the secret value that we think might be interesting yet. Oh yeah, that's because I haven't. Let me just hit continue if I hit the other breakpoint. So right now it's just going to ask us for input. Again, I'll just go password 1234 because that's got to be it, right? And then what I just typed before was the C for continue. It just means continue until you hit another breakpoint. So now we've hit the instruction that we've set the other breakpoint at, the as secret. Let's just check what's in our registers right now. You can see RAX and R8 both have password 1234, which is what we kind of gave in as our password because we don't really know what the password is right now. So we can just go ahead and use SI to just step past this instruction. And let's just see what got put into RDX. So we scroll up and you can see it is a string. It's a kind of a long string because it doesn't fit entirely on what Jeff is showing us, but just goes a bunch of pretty, please, etc. So if we want to look at the entirety of the string, we can use that X functionality we were talking about earlier, and we can just do X/S, S standing for string of, sorry, this address in memory. Which, yeah, it is a string. It seems to be the password is pretty, please don't blow up. And you can tell that's the password because they do the comparison on that string specifically later, because you can see RAX is moved into RDI, RDX, which has our user input, moved into our SI, and then string comparison is run on those because those are the first two argument registers. Cool beans. All right, since we know that's the password, we know we got it wrong, we're just going to kind of stop our program and start again. So let me hit Control C. Our breakpoints stay the same. I'm just going to get rid of breakpoint 2 because we no longer need it since we know the password. And then I'm just going to instead set another breakpoint at, I think we're going to pass this time. Sorry, 1 second. I'm just going to set another breakpoint right, here. And I just realized copy pasting that has lost me the string, so I'll have to save it somewhere later. Any questions about like the logic behind why I did what I just did? Anything? If you have questions later, feel free to ask them. Let me set this breakpoint really quickly and let me go copy that string again because I forgot it, or actually I could just print it out again. And let me just save it in my notepad. All right, just so I have that for later. And then let's just run the thing again. All right. We'll hit continue. What's the password? You think we got the password right? We good to go. Let's find out. I just realized I forgot to set a breakpoint in explode. So let's hope we're right. And we are right. You can see we've hit main 122, which is where the jump would have gone if our two strings were equal. So we got the first part right, but there is still more to come. So let me set a breakpoint and explode right now while I remember. All right, cool. Okay, so now we can just kind of stare at this code a little bit more just from a static point of view, because it shows the entire thing. And now we only need to kind of worry about this bit of the code. We've kind of passed everything else. Assuming we don't have anything that'll jump us all the way back to the beginning, which we don't. You can look through and just confirm that for yourself manually, but I know we don't. We don't have to worry about anything that's up there, right? Okay. So you can kind of see again, it puts something onto the display. It asks us for something using fgets. It runs this ATOLL, I don't know how to pronounce it, ATOL function, which is a C function. I'm going to tell you right now, like if you recognize it, if you see a C function, you don't recognize it, look it up. But like if you do more of this stuff, you'll start to recognize the C functions. What this one does essentially is if you're given like a string input or something, and like your string input can be parsed as a number just by staring at it. So like say you type in 53, this function will go and it'll convert that to an integer. But if you type in something that's not parsable as a number like cat, it will interpret it as 0. So that's a functionality you can look up online. It's functionality that like you will remember over time. But yeah, so it seems like it's asking us for some sort of number because of this ATOLL call. It's moving the results of that into some location in memory. And then it's moving that later into RDI and calling this magic function on it. And then I guess we want the magic function's result to be 0x16. And then if it is that, we will do this jump. If it isn't, we won't. Cool. So what is magic? We'll just look at that as well. Okay. So this is kind of where control flow graphs might be something that's cool, particularly because we see we're doing this move, and then we're doing a whole bunch of different jumps. We can kind of try to parse. Does anyone want to try and parse this through by hand? Crickets, dead silence. No one wants to do it by hand. You can do this by hand. You can go through and you can look and see what's happening with all of this stuff, where we're jumping to. You can kind of see we're jumping to some location that is a result of whatever value is in RAX plus this address, like whatever value is in RAX times 8 plus this address, and we're jumping there. I don't want to do all of that math right now, so I'm not going to do all of that math. We're going to look at the control flow graph. Sorry, let me open Cutter again. All right. Also, I'm going to ask again, does anyone have questions on the first part of that? Which, if you want to follow along with what I'm doing, you can go to platform.acmcyber.com and download Minibomb off of there, and then just walk through it. But yeah, we're going to open Cutter again. We're not going to load it in write mode because we don't need to write anything, and also because since we have it open, it's probably not going to let us. And we're just going to wait for it to do its thing. And then we're going to stare at main real hard. So you can see this is kind of, let me close this out so we can see better. Let's see. Okay, I don't think I can show the entire thing on here and still get the big picture. But I'll just kind of zoom in and talk about each individual part. And we could also maybe draw it out if you want. But you can see right at the beginning, we have all this stuff that's happening. We're not going to think too deeply about that right now. We'll think deeply about it later. But you can see this is kind of formatted like a switch statement because it is a switch statement. If we want to later, we can go ahead and take a look at this instruction over here, this move Q. And what that does is actually checks our switch table and it'll go to the location indicated at that switch table. We can look at it in memory later in GDB, but Cutter does that automatically for us and then creates a control flow graph based off of that. So this is a switch statement with 6 cases. You've got case 0, 1, 2, 3, 4, 5, and then the default case. And then what each of these cases seem to be doing is they seem to be modifying this var.ch in some way, which var.ch, this is something that Cutter does, I think Binary Ninja does this too, is it'll just set like, it'll alias like stuff like this, like stack minus -c, like positions on the stack, to variables to make them more like easy to read. But what's happening is essentially this var.ch is being set at the beginning up here to 0xa, which is 10. I'm very good at my hexadecimal conversions, if you couldn't tell. But yeah, essentially what's happening is each of these cases seem to be manipulating that thing. So the thing that's originally 10, it's either moving stuff into it, like you can see here, we're moving -1. It tells us it's -1, by the way, shout out, so I don't have to do hex math. It's moving -1 into that location. In case 5, it's moving 1 through 3, 7 into that location. Here it's moving 42. Right over here it moves 0. And then these cases 1, 2, 3, there's actually some like manipulation being done. Case 1 does like a regular move, but case 2 will do like an add of 1 there. So if it was 10 there and we went to case 2, it would become 11. And case 3 does a shift left, which essentially what shift lefts do is they just double stuff, taking all the bits, shifting them to the left by 1, binaries and powers of 2. So if you shift stuff to the left, it becomes 1 power of 2 higher. Yes. So yeah, we have all of these different cases, and something that you might remember from earlier, if you don't remember, though that's okay, is that if we check out main again, after we did this magic call, it wanted the value in EAX, which EAX is a return value register. So whatever magic returns, it should have been 0x16, which is 22. So essentially, we want to kind of use this control flow graph to figure out which of these cases will result in this value, var.ch, because also you can kind of see right here, var.ch gets moved into EAX. Sorry, I forgot to mention that. But we want to see which of these cases will result in var.ch ending up as 22 at the end, so that we can pass our jump and move on with our lives. All right. So just by looking at this, we can just start off with a default case. Default case moves -1. Does that seem right? No. Thank you. It's like my discussion section. But yeah. That doesn't seem right. That's also something that we can confirm by staring at this big block of text. Just as magic. We can also confirm that by staring at this big block of text, because you can see, we're not going to look at the jump table right now, but just take my word for it. It would take you over to here, and it would move this -1 into this right here, which is the location on the stack we're thinking about. You can see it. It's kind of a pain to look at. Even if you were doing this like this, you'd probably want to be drawing something out like manually or to the side, unless you're really good at just looking at linear assembly and just knowing what it's doing, in which case respect, because I can't do that. But yeah, that doesn't seem right. We can rule that out. Case 5 moves 1, 3, 3, 7, also not right. Case 4 moves 42. That's also not 22, but it's a little closer. And then case 0 moves 0, which not correct. Then we can kind of talk about cases 1 through 3 now, because this is kind of interesting. You can see they all fall directly into each other. You've got like these arrows that, and by the way, sorry, the arrow highlighting is a bit different for here than it is for Binary Ninja. The greens are the unconditional jumps, and the other ones are just highlighted like normal. Not as pretty, but it's open source. That makes it cool. But yeah, you can see cases 1, 2, 3, they kind of fall directly into each other, which means that there's no break between them. Well, there's a break at the end of case 3 because we move straight down to here, but there's no break between cases 1 and 2 and cases 2 and 3. So if we decide to go to case 1, all cases 1 through 3 will happen. If we go to case 2, all cases 2 and 3 will happen, etc. All right, so knowing that the value that we have in var_ch is 10, and we want it to become 22, where do y'all think that we should go to? Case 2, that's about right. Because if we went to case 1, we'd move this 1 in first, add 1 would make it 2, double it would make it 4, that's not right. But if we go to case 2, add 1 makes it 11, shift left or double it makes it 22, and that's right. So that's pretty cool. We've kind of figured out just by looking at this, we want to move to case 2, but what do we put into our program to make it case 2, right? Sorry, I'm going to start coughing. We can kind of keep looking at our control flow graph for this, and I can just talk to you about switch statements real quick. But the way switch statements generally work is that they move this, like right here, there's a number, it's a big negative number. You can tell because it's got F at the top. It's moving that into RDX. And then it's kind of adding RDX and RAX. Hang on, it's kind of, where am I? Move that into RDX. Yeah, moving var20ch, which here it's RDI, it's moving the argument we passed in to RAX, adding them together. And then basically, its goal is to kind of zero out like whatever number we gave it. So like, not zero out, but its goal is like, let's say you have a switch statement on like the numbers 60, 61, 62, 63. Its goal is to kind of make those in the form of like the numbers 0 to 3. So essentially what it'll do is subtract 60 from all of them, and then you'll be left with case 0, case 1, case 2, and case 3 instead of case 60, case 61, 62, and 63. Do you guys understand that? If you don't, I can talk about it more. Okay, feel free to ask me later. But yeah, essentially it's moving this big negative offset, and then our goal is to get the positive number that will result in this negative number plus our positive number being equal to 2, because we want it to go to case 2. Solid? Yes, no, maybe so. All right, we're going with yes. All right. First of all, I don't want to think about what this big number is because I'm not good at hex math. So we're just going to do print/decimal, which, by the way, P, we didn't talk about this. P stands for print. It's what you use if you're just trying to talk about like literals or whatever. Printed. It's this negative number, negative 1337, 1337, 13370. And then we just want the number that when this is subtracted from it will result in 2. So we can just replace this last value with a 2. And then what that should do is that should theoretically get magic to return the value of 22, and then main should be like, that's cool, that's what we want, the jump equal works, and then we skip right past this explode column called defuse. Are we good to try it? Questions, comments, concerns? Ask later if you have any, ask now if you have any, that's fine. I don't remember if I'm running this right now, actually. Okay, I was running it. All right. Cool. So then this is the number. We want case 2, so I replace that last digit with a 2. And this should work. I messed up. Oh no. Oh no. Oh, because I forgot to get rid of the negative sign. Oh, that's my bad. We're starting over. Sorry. Moment of glory vanished. Let me take that. That was supposed to be really dramatic, and I kind of flunked. Pretend that never happened, okay? We're gonna cut it. We're not gonna cut it out of the recording. Thank you. Exactly. You're so right. All right. We're gonna start that over. Password. We've got the password. What's my favorite number? This is the right number. I didn't forget the negative sign. This should work. It works. So essentially, that's the right number. We did it. Using Cutter, we were able to kind of go ahead and walk through that switch statement without actually thinking too much about it. and we defused the bomb. If you want to try this stuff out on our challenge platform, then you'll be able to get the actual flag, and the challenges are worth 30 points on that platform, so you get lots of points, lovely points, free points. But yeah, does anybody have any questions on the tools and the features I just kind of showed demonstration? We don't really have much else after this on the presentation, so feel free to ask me more later. Otherwise, I think I'll just finish up the presentation on here, and then we can go ahead and do cool challenges. Oh man, I have so many windows open. Oh Jesus. All right. And then right over here, I kind of copy pasted. This is the control flow graph for main. It didn't all fit on here, so I had to make my own edits. But control flow graph for main. And then this is the one that we just kind of talked about for the switch statement. You can see it all in full here. You can also open up Cutter or Binary Ninja and look at it yourself. It'll be relatively similar on both of them. But yeah, after that, we're done. Do you guys have any questions? All right. Well, in that case, it is challenge time. So feel free to go on over to platform.acmcyber.com, and we should theoretically have challenges up. Thank you, Jason. We have challenges up. Feel free to ask for help. Try them out. Try out some of the stuff that you just learned. If you didn't learn anything new, just try out some of the stuff you already knew and practice, get better at it. Have fun. And yeah, thank you so much for coming. Check out our link tree with all our socials and information.